storage is full. Okay, they say it will be over on the 16th, but today is not the 16th yet. So, and then I will clean the space there. Okay, so multiple dipoles and multiple time slices, right? Still, when we say multiple, it was равно, sorry, nevertheless, sorry, I'm in bad shape. I went to bed very late yesterday. It was nevertheless very few dipoles, very few. Okay, but nevertheless, there were dipoles. You could feed parametric model of dipole. You could identify the location of the dipole, orientation, and you could identify the time series of each dipole. And you were not restricted to working with, let's call it this way, with a single slice, right? But you were working with a window of data, and you used the music family of methods for that, right? And then we did the next step. We said, okay, now we want to, and yes, and in these both cases, we were looking for a global solution. Okay, that was a global solution in a sense that the dipoles and the time series of these dipoles, when projected back onto the sensors, they had to, or at least we wanted them to, explain the observed data. Okay, so they want to basically, ideally, when you subtract the synthetic data, those which produced by the dipoles with the time series that you found, and you subtract them from the data that you have recorded, you get zero. Okay, but of course, you're not talking about zero. We are talking about the lack of any structure. So the noise has to be structureless. Okay, after you have subtracted the two. Okay, but then we said, okay, well, let's just make some transition, make some fun, and let's go into the. If I make also, of course, I'm about fun. Let's look for the non-global solution. Let's try to listen to a particular source. Okay, let's say choose a source, and given that we have sensors recording the activity, let, I don't know, something like this. Well, anyway, let's do a brain. Yeah, so consider a source and then sensors around the head, and then you said that, okay, if I'm listening to the source, if I know how the source projects into the sensors, which is my forward model, right, may I set the problem that I will create a set of coefficients which I will use to combine the signals of the sensors with, so that I can listen to the source and subtract the activity of all other possible sources. Okay, so that was the solution of the form W transpose X of T, right? Where W was your filter, and that was a beamforming method. Okay, beamforming, and we called it LCMV, linearly constrained minimum variance beamformer, because in order to listen to this particular source that has topography G, right, GI, for instance, then we were imposing the linear constraint that the gain at this direction is equal to unity. Okay, and asking to minimize the expected value of this guy, right? Square. Asking to minimize this guy, which is equivalent to CXW, to minimize. We were trying to suppress the rest of the sources. Okay, that's beamforming, and we didn't care in this approach. We didn't care about explaining the data. Okay, all we care is just let's listen to a source based on the data, and then we said, okay, but you can still do a scanning across the entire head. So see, it's a very different approach here, right? So we are not looking any longer for dipoles and for their parameters, right? But we rather select the dipoles imperatively for each location, you know, on the cortex that we have, and then we scan, measure the output power, right? So basically this power that we want to minimize, but nevertheless we measuring it for each location in the brain, and then we plot the profile of this power. We will do it now in the script. We will plot the profile of this power, and for instance, receiving something like this, which tells us about the presence of the source at this location. But we do so only after we have scanned through all, basically looked at every time slice, every location in the brain, and did it. And now talking about the temporal extent, where we measure this power, we of course can measure the power at a single slice, right? Just a single slice, or we can measure the power within the window, within the time window. We are free depending on how we compute the CX, okay, the covariance matrix of the data. Okay, so and then I mentioned to you that once you have scanned, you have obtained, of course, some scan, and you will see this example today. But the scan is typically gives you a biased location. So if you look for the maximum as an estimate, a maximum of the power after such a scan, as an estimate of the location of a source, then you will be biased. You will get a biased estimate, and very often sources will end up in the center from this, in the center of the brain. This is because the deep sources have weak G, right? Small norm of forward model, because they're weak, right? So the amplitude is very small, right? That you receive after, if you activate the source that is located deeply inside the brain, then what you see on the sensors is relatively small compared to if you look at the sources that are close to the sensors, right? Then when you do beamforming will try to compensate for this and artificially emphasizes them. Okay, so and in order to deal with this problem, I was suggesting to use a neural activity index, where we would compute covariance matrix on the pre-stim, and we compute the covariance matrix of the interval of interest. Okay, let's say this interval C post, for instance, and then basically estimate the power with beamformer using this covariance, which is post-stim, and divide it by the power estimated during the pre-stim. Okay, this way you will remove the bias due to the depth, due to the spatial properties, right? But you will only be measuring how the signal in the given location changes when you compare it after the stimulus presentation in this time range, or before the stimulus presentation when nothing was happening. Just hold on a second, I close the door, okay? Just a second. Yeah, okay. So, all right. So, and let's now play with beamformer a little bit, right? So I will just before we do this, however, I will remind you. So after minimizing this guy, which is output power, beamformer output power, right? With the constraint or whatever, doesn't matter. W transpose G sub I equal 1, we arrived at in the simplest case, we arrived at the solution Cx minus first G divided by G sub I transpose Cx minus first G, right? So that was your Wi vector that you need to apply to your data X in order to measure, and then measure the power, right? Or you can apply it to the covariance matrix itself on both sides, right? And measure the power. And this is the scan. This is this is beamformer scan, okay? This is beamformer scan value for the eyes cortical source. Okay, source. Okay, so let's try and see what we can do based on this. But yes, so hold on, yet another thing. But then we looked at so-called vector beamformer, okay, when we started to recognize the fact that we do not really strictly know the orientation of the source, right? And then we were saying that, okay, in each location we are beamforming in fact for 3 dipoles, okay, each orthogonally oriented, and this dipole has topography GIZ, this one has topography GIX, and this one has topography GYY, okay, for example. And we found that in this case, we need to formulate slightly different solution, but again, according to the same principle, according to this Laplace principle, right? Lagrange, sorry, according to Lagrangian, right? And so we said that when you formulate G as GI, sorry, let me do it consistently. GI, GIX, GIY, GIZ, okay, these are 3 topographies. And then our solution was for the 3 vectors that are tuned at GIX, GIY, GIZ, right? At 3 orthogonal sources in this ice location. This was already a matrix, and we had to do this. We had to take GI, we had to take CX, I'm writing badly, CX minus first. You have to take GI, here you have to take transpose, take inverse of this, and multiplied by CX minus first GI, okay? So, and that was your filter, okay? If I didn't make mistake, but I think I did make mistake. That was, this is 3 by 3. Yes, let's remove it here. So you have to, it has to be GI transpose CX minus first, something like this. Or you can move it to the other side, but doesn't matter. So that pretty much that's the solution. And here is an important thing. Why the reason I mentioned it, not to complicate it. But in this case, of course, because the beamformer is quite sensitive to the forward model accuracy, if you were in this case specified the topography of a dipole corresponding to your own orientation, then you probably would get significantly weaker activation due to the fact that beamformer will try to minimize the output power while satisfying this constraint. If this constraint would use G sub I, which is not truly the G sub I that is in your data, right? Then it will very happily satisfy this constraint, but will minimize the output power. So you understand, right? If I tell you that I want to listen to the particular direction, and if I misspecify this direction, right, you will try to provide gain 1 on this direction, but this will be not the direction equal, let's say, it will be not the vector describing the signal coming from the angle, let's say 30 degrees, right, if you talk about acoustic radar, right, but it will be something, a vector specifying it from 35 degrees, right, and you're thinking that you are beamforming to the source that is located 30 degrees azimuth from you, for instance, but in fact you are beamforming to the source that is located at 35 degrees, which is 0, okay, which is not present there, right? And therefore you will get signal weakening, signal cancellation at the output of the beamformer. Therefore it's very important to use the triplet of in MEG duplet of dipoles at each location. But if you use it, you will arrive at this thing. See, you will, once you apply the W, right, W is a or maybe, yeah, W is hold on a second. I think let me rewrite it here. So I think because I think this is just wrong. So yeah, CX minus 1 G hold on, CX minus 1 G, right? This is CX minus 1 is number of channels by number of channels. G is 3 by 3. Yes, multiplied by GI Cx minus first Gi minus first. Yes. So that's right. And this is your W, and you will be applying W inverse, right? So you will be no W transpose, right? W transpose to your data, to your X of T, right? And as a result, you will get the time series of S or X of the dipole oriented along X axis, of the dipole oriented along Y axis, and of the dipole oriented along Z axis. Okay. And then you have these three powers basically, right? If you apply, if you say, if you make it W transpose multiplied by CX multiplied by W, you will get a 3 by 3 matrix, right? It will be 3 by 3 because you have W, which is 3 elements of W, right? Each store in X, Y, and Z direction. And what do you do with this? Okay. How do you show it? How do you make a decision about what is actually, which power is actually there, right? So there are two things, two ways. The first way, you can compute the trace, basically sum the diagonal, 3 diagonal. So basically sum the powers in all in all directions, in all the 3 directions, right? Or you can take the SVD of this matrix, singular value decomposition, and take the first singular value which describes, which corresponds to the basically, which would describe the situation if you had really a single dipole, but you don't know exactly its orientation, and it's fixed, this orientation is fixed, then this first singular value and singular vector, which singular vector would tell you about the orientation itself, but singular value will tell you about the power of the dipole. Okay. You don't have to really in details understand it, but I'm just telling you because we will be using SVD in the code so that you understand, right? Because basically we are looking for such a vector that when multiplied, so if this is matrix, let's call CS, okay, this is a power of the I source, this covariance matrix basically of the I source already in the sensors in the source space, then you are looking for such, let's say V transpose CSI, right? And then V here, right? For instance, you are looking for such a vector that will give you the maximum possible value. Okay. It means that you are, in fact, you are with the 3 dipoles, you're somehow seeking for the direction which will point into the direction of the largest variance. Okay. So and this is efficiently done with SVD, or in this case eigenvalue decomposition, which is the same because the matrix is symmetric. Okay. So yeah, let me now stop sharing this thing, and let me share the other screen. Okay. By the way, look at this. This is beautiful. Do you know what? You probably know. Yeah, this is Mini Pig. Yeah, I could have made it. I could have teased you, but yeah, it's Mini Pig's brain. It's beautiful, isn't it? Mini Pigs. Look at that. Look at this. This is amazing. Yes. Anyway, let's go to the brainstorm, to the whatever, to MATLAB. So you can see my screen, right? All right. So again, the same story. We have loaded the cortices. Well, first the file names, loaded the cortices. Then I have this. I just simply wrap this into a more compact thing, so that I'm just simply preparing the forward model for the high resolution cortex and for the low resolution cortex. Actually, we will not use high resolution cortex today, but just for yes. And then let's say we are we choose simply, I don't know. Well, yeah, we just choose 2 sources. Okay. So the source with index II, a source with index JJ. Okay. And then they have certain coordinates. Okay. So the coordinates of this source, this will be, sorry. Copy. The coordinate of this will be II is this. This is in meters. Okay. 10 centimeters, 16 centimeters, and 16 centimeters front and 12 centimeters up, right? This is for one source, and for the other source, the same pretty much story. Okay, so but Yeah, slightly different coordinates. Okay, so and then let's find this. Let's generate the time series. Okay, so but in this case we will use the pre-steam and post-steam intervals. So I will plot them, and then you will see what I'm talking about. Okay, of course this is not the most elegant way the simulation should look, but just for simplicity. Okay, so this is the post-steam. Okay, this is the activity of two sources. Okay, one source, another source. And this is the pre-steam interval where there is no activity, ideally assuming no activity. And then we add some noise to it. Okay, so we get again pre-steam interval and we get post-steam interval. Okay, and then what we do based on the recipe or beamformer recipe, we first calculate the covariance matrix for the pre-steam interval. Okay, so we just take the pre-steam interval, multiply by its transpose, and divide by the number of time slices, right? And the same thing we will do for the post-steam. Okay, so here is the code. So we divide by the number of time slices, okay? But what we do, we take x for the interval of pre-steam, okay, and multiply by its transpose. So efficiently, we're then accumulating the outer products, which will be the diagonal, and cross products of these guys, right? So let's do this. Okay. Sure. Yeah. Yeah. All right. Then let's do this. Figure. The image you see. Let's look at these guys. R pre, R post. Yes, that's what I meant. It's very smart. See, almost like ChatGPT. All right. So, well, clearly here, well, I mean, let me better display it differently. Let me separately display R pre, and then let's take new figure and display R post. Okay, and then color bar here, and color bar here. Okay, so see. I'll somehow try to move it. Yeah, so look at this. Disregard the small values 10 minus 12 minus 12 minus 14 because we are talking about MEG here, and the forward modeling gives you values like femtotesla. Oh, this is Tesla basically, right? 10 minus 14 Tesla is 10 femtotesla. Okay, so anyway, but and also this is a square, yes. So not even disregard these ranges. I mean, just disregard them, but just compare them. Compare. So this is a covariance matrix with two sources active, and we can see that they're present here. But on the top of these sources, we see the general structure that is there, where we see some maybe noisy sources here, and that's how this covariance looks. Okay, so basically each of diagonal element here tells you the correlation of one sensor with another sensor. Okay, so we had 102 sensors here, and yeah, that's basically it. And the diagonal tells you about the power of which activity in each sensor. Okay, so you can see, for example, that activity in some sensors is anti-correlated. Sensor like 27 or something is anti-correlated with sensor 40, right? And on the contrary, activity of the sensor 40 is correlated with the activity, it's positively correlated with activity of the sensor 47 or something. Okay, so that's your covariance matrix. And the covariance matrix, as I already mentioned in the lecture, contains information about the spatial content of your data. Okay, about the what is present in your data, right? Because the column space of this matrix it basically forms so-called signal subspace that we used when we were doing rap music or whatever, right? So we can take, like, as I mentioned already, we can take SVD of this matrix, for instance, limit first few left singular vectors corresponding to the largest singular values, and those vectors are most likely will span the subspace of topographies of our sources. But of course, which source we will not know. We will not know exactly the topography, but we'll know the subspace, right? But we are not using this in the beamformer. Therefore, I'm just to mention it. Okay, now this step is to add some regularization, to add a little bit of diagonal to this matrix, so that when we invert it, we don't have problems with stability, okay, of the inverse, because it's usually this MEG, EG data are rank deficient, and inverting them leads to numerical problems. You can either use pseudo inverse there, or you can do this what I've just done here. Okay, so just simply raise the diagonal. It's very similar to this ridge regression story, where if you know machine learning a little bit, then you have this technique called ridge regression. In Russian, is гребневая регрессия, meaning that there is this ridge of the diagonal matrix that you want to raise. And I'm sure, like, if we showed now, let's do, let's look at this matrix after diagonal has been raised. You will not even notice it, right? But it's slightly raised, it's slightly higher than it used to be. Okay, so anyway, now what we will do, we will compute the inverses. Remember, in this formulation of beamformers, we have inverse of this covariance, right? And remember this whitening story, that why this inverse happens, right? Because we are, in fact, whitening the data, and to whiten the data, we need to multiply them by the square root, by inverse square root of the covariance matrix, right? Of this data, yeah. And then let's for each source sensor location. So we have for each source location and sources we have, right? And sources in this model, we have 5,000, okay? And then for each source, we take the triplet of forward model vectors, okay, with topographies, right? The three dipoles oriented in three orthogonal orientations, right? But corresponding to a single location, single point, okay, here. Okay, so we take this and we compute the beamformer weights. Okay, I use spin here, not because otherwise I should have added lambda I, due to the fact that we are dealing with MEG data and MEG forward model, and matrix G, as I already told you, because it's rank deficient. It has only two non-zero components, and the third component is 0 because it's a forward model. It's a sphere. Right, and for the sphere, for the radial component is vanishing, right? The field from the radial component is vanishing. Therefore, but just to avoid extra symbols, I just use pseudo inverse, and that's it. Okay, so okay, we computed the weights, the beamformer weights. If you look at these matrices, you will see that they're of size 15,009 by 102. Okay, so you have each vector is 102 long. And you have 15,000 of them because each triplet corresponds to a single source. So you divide 15,009 by 3, you will get this, right? Because you have 5,003 locations, and per each location, you had 3 constraints. And for these 3 constraints, we got 3 vectors in vector beamformer, right? Those that I just mentioned in the beginning of the class, okay? So, and then we will do the scan. So first we initialize it again. And then again, we are moving for each source, but we are moving with triplets, right? So we are moving with these triplets. We extract first post-steam weight matrix, beamformer matrix, compute the power at the output, right? This W times covariance matrix on the post-steam times W, right? This is the power on the entire interval in this case. Then we take SVD of this matrix TMP, and we select we assign as the largest singular value to the value as a value of the scan. Okay, then we do the same thing for the pre-steam. Okay, the same thing exactly, but just pre. And assign again, do SVD, and then assign the largest value to the the QS, or the largest single value to the scan with pre-stimulus, and then increase by 3, moving to the next source. Okay, so let's run this. Let's run this pretty fast, of course, and then let's just plot it linearly. Let's plot the scan linearly, so that each source is simply, you know, it's simply x coordinate. Okay, so it's just the scan. Okay, so let's remove this. let's plot this, and we will plot the neural activity index, which is the ratio of no. Yeah, first let's first just scan plot scan on the post-stim interval. Okay, let's plot it. Okay, see, we have simulated two sources. You see the two locations where you have maxima, right? And you may say that, wow, that's so great, that's so neatly has identified them, but this is not true because these sources are not the true sources. Okay, these sources are this is due to the problem of the biasedness of this estimate, and they pertain to the center of the head, in fact, as you will see. But if you plot now, if you on the same plot, if you plot the normalized this index, right? Let's do it this way. Let's call it NAI, and neural activity index, which is the ratio of the post-stim to the pre-stim. And I just added 0.0001 to avoid dividing by 0 in case there are zeros there. Okay, so, and then I just plot it to normalize it so that I can plot it on the same axis. Okay. All right, now. Yeah, and now you can see the red one. The terracotta one is the proper scan. So here are the two sources. Okay. And they're proper. I know that they're proper. I will show you, but those are, but that would be estimated if you don't do this normalization. Okay. And without the normalization, you will find the central sources, because I just know that these two sources, they will highlight in the center of the head. Okay. Now let's plot normally how we used to. F9. See. Okay. Here is the scan. This is already normalized scan. Okay. So I plotted this ratio. See, Q post-stim, Q pre-stim, right? Those are some source locations with red, and you have maxima exactly at these source locations. Okay. But if you were to do very similar story, but only the post-stim, let me make another figure here. If you make the post-stim, unfortunately, I tell you that I have very weak video card, but if you were the activity is there in the center, you just can't see it very well. A little bit here, but not well. See the scan is basically is given you very see, there is, you can see it's a little bit transparent, so I don't know if you can see it, but there, see my mouse here, right? So it's in the center of the head that you get this activity. Yeah. Okay. Sorry, already too much. Yeah, here, which has nothing to do with location of your true source. Okay. So unless you do this kind of normalizations through neural activity index, you shouldn't use beamformers. Okay, in general, in practice. Okay. So now let's look again at the scan. No, not at the scan. So here we can see that both sources were located quite nicely. So the scanning procedure as having, what does this mean? What we located them with neural activity index? It means that we measured, we beamformatted them, right? We learned to listen to them, and then we compared the amplitude or the power of activity of these sources on the post-stim interval divided by the pre-stim interval. Okay, and that's what we have obtained. Okay, and that shows us this increase, and in fact, see how high resolution it is, how narrow the peak is. And I didn't threshold it. If you remember rap music, remember what rap music was given? It was like blob like this over here, right? And with only very high threshold, you were able to see it. But here, I have this threshold is 0.01. See, so it's like almost no threshold. I can put no threshold, and see, pretty much the same thing, right? So it means that there is a very high contrast between the activity between the scan values and locations of the true sources compared to the rest. Okay, so, and we can actually try and we can try to break it now. Okay, let's try to break it because it's too beautiful, right? Let's make it a little bit. Let's make time series. There is a problem with beamformers if you have if the time series become correlated, okay, too correlated, then they will fail. Okay, so let's try to make it more correlated. Okay.
Time series
Yes,
of what?
of the sources.
Of two sources.
Yes, of the two sources. Yes, this remember we had this. Let me show you. We had this. We had this, right? They're
If
not.
they will be
They're not
closer, you
really.
mean?
Yeah. They're not really correlated, right? They're kind of shifted. So if you make the red one and the blue one closer to each other, the beamformer will start to fail. Okay. So let's try to bring it closer. So see, this is a phase difference between the two. Okay. It was used to be 0.5 pi over 2. Now it's pi over 10. Okay. So I'll just initialize everything here. So that should do this, and then plot them. All right. Now it's better, right? Well, I mean, it's worse for the beamformer. Okay. So, and then do the same thing. We will have to, of course, do the same thing. We'll have to recompute the covariance because everything has changed. You have to compute the scan. And let's see. All right. Okay, the scan is done. And now let's do the plot. Let's plot the neural activity index right away. See, things are getting worse, right? First of all, we see this diffusion here, right? Second of all, we don't see the second source almost at all, right? And this source, well, we can see it, but it's not that great. It's not as great as it was before. Let's make it further. Let's try to break it next further. Let's make it like 0.01, for instance. Very synchronous. This happens when you, for instance, place something into your ears and look for the activity of the primary sensory auditory cortex. Okay. Okay, that's see, they're very close, right? And then see, that's it. It's gone. Okay. So that's it. Beamformer is helpless because what happens is actually color bar on the previous plots would help. Let's just do this. You know, let me do this. Let me add the color bar here. Okay. And let us go back 2.5 Ks. Okay. 2.5 pi K. And then let's not kill anything. Okay. Let's just simply recompute everything. And it is slow, not because it's just because it's a very, very inefficient implementation, because I was not, of course, running for the speed here. And then do another figure and then color bar. Okay. The only thing that we are making this neural activity index, therefore maybe it's not will not be as pronounced. The ratio, but maybe yeah, but still it is. So see what happens. So why we have this diffusion? Why we don't see the sources? Because what happens is that see first of all, let me try to explain. So you have the distribution of this neural activity index, which is the ratio of the power during the post-stim divided to the power during the pre-stim. Okay. So, and in this left plot, you see that this ratio is about 90. Okay, well, in the highest source, right? And for the smaller source, like it's about like 40 or something, right? So maybe 30. Okay. In the case of synchronous sources, all those amplitude of sources didn't change, right? We didn't change the amplitude. We just made them more synchronous. The output, see, the ratio is 3. At the highest ratio is 3, and it's somewhere in the center of the head. Okay, so it has nothing to do with actually. It's actually, if you do some statistics, you would probably find that this 3 is not significant at all. You know, it's just basically. So see what happens. What happens is that the output power of the beamformer dropped, and this is so-called signal cancellation criterion, and it's a well-known fact that the beamformer, when it's operating in the environment with correlated sources, will tend to underestimate the power sources. You can derive it. It's actually very straightforward to derive it, especially if you use some symbolic math toolbox in, I don't know, you can use some Mathematica, or you can use in MATLAB, because just too many, there are some manipulations, but it's trivially done. You know, you just define the covariance matrix, specify the covariance coefficient, the sources, between the sources, and then find that the output of the beamformer is in fact 1 minus, proportional to 1 minus rho squared, where rho squared is the correlation coefficient of the time series. Okay, so clearly if rho is 1, then the output power is 0, right? Okay, so why this happens? Well, I tried last time to explain this, but it was the end of the lecture. I may try to iterate a little bit because I think it's important, and I will try to be intuitive. Okay, so see, the beamformer is basically a slave, right? That you're asking to. This is, you know, be careful with what you wish, right? It may come true. That's exactly the story. Okay, so you want to listen to a source at a given location, at a given direction. Okay, you don't even have to think about the brain now. You can think about, you know, acoustic radars or location, maybe the direction at which you are listening to, right? So you ask it to listen to this direction. To basically, how do you ask it? Well, you formally say make gain 1 in this direction. So W transpose times the forward model, because in acoustic radar there will be also a forward model vector, right? But it will be different. The forward model is 1, so that you always listen to it with gain 1. So the sources which are active at that location will arrive to you with gain 1. But that's not the whole story. Okay, the next step is you're asking to minimize the output power. Okay, so, and then beamformer, what it does a very, very obvious thing. If there is a source that is correlated with your target source, okay, so if there is a source which is correlated to a target source, the beamformer can be smart, and it can provide gain 1 in this direction, in this first source, but the vector does not have to align with this vector, but it can be checked, it can rotate it such a way that you will pick up the power of this other source, okay, and subtract it from the beamformer output due to the activity of this first source. Because it's synchronous, it's exactly the same shape and time. You can take it and subtract it from this one. And once you've done this, the output power will be small, but the gain will be 1, because regardless of how the vector is a W is away from your G, right? From your constraint vector, regardless of how it is, as long as it's not orthogonal, you can always scale W to make sure that W transpose G is equal 1, right? It can be like almost orthogonal, but you just scale it and it will be 1. So the beamformer will satisfy exactly your request. It will provide gain 1 at a given location, direction, and it will minimize the output power. So that this signal cancellation comes because appears, or, you know, exists because of your constraint, because you are the master of your own life in a way, right? And you've got what you asked for. Okay, so there are ways how to deal with it. Of course, we have a paper recently with my PhD student. It's called Ariadne-Psikas beamformer or whatever. Don't read it, it's very complicated. So, but anyway, so this beamformer basically is, this new method is trying to somehow to make surgery on your covariance matrix, because information about synchrony is in your covariance matrix, of course. Somehow make the surgery on it and remove the contribution of the synchrony thing. Okay, so but other solutions exist. If you, for example, know, if you're talking about like auditory responses, right? the first solution would be is to put explicitly 0, add additional constraint, say WG right, because right here is 1, but WG left for the homologous region on the left, right, is equal 0. Therefore, you will tell beamformer, don't listen to that. Don't use this guy, okay? Because if it wants to use this guy, it has to somehow turn the vector along this guy. But you say, no, it has to be orthogonal. And then beamformer will behave better. I'll not experiment it here because I didn't prepare this code for you and it will waste your time. But so there are ways, but you need to know where the interference source is. A. B, the fact that the fact that the brain is actually activity of the brain, right, comprises many sources that are actually synchronous sources, right? They're synchronous because they may be involved in bidirectional communication, you know, the two sides, and then the phase becomes close to 0. Or, as I said, they're driven by the common stimulus. Also, they exchange information all the time, which requires synchronization between the time series. Of course, it depends on the lag, right? And that's how strongly they're correlated. But anyway, it is very, very likely to say that very, very true to say that the brain activity, the sensors, the sources of the brain active and are pretty correlated between each other. Okay, so therefore the beamformer, although it works surprisingly well, especially if you're provided with this neural activity indexing, right? You have to be very careful because the beamformer, you don't really have to, as we show in this paper, you don't really have to have like source which is very well correlated to that other source, right? You can have sources with many sources which are kind of correlated to the source, but everyone differently, right? And then the beamformer will try to collect the activity of these guys to cancel, to minimize the output power. Okay, so that's you probably heard that in this radar story in the military usually thing, when you want to suppress enemies against missile system, for instance, or anti-missile system, and if you can generate the activity which is similar or synchronous to the activities that is coming from your targets, right? If your plane is flying over and you know where it's flying and you know which signal would be reflected from it, right? You can simulate it with some jammer, right? You may have a jammer somewhere which generates synchronous signal, and then this radar will not see the plane, okay? Because the signal will be canceled because the adaptive beamforming algorithms are working there, okay? So, and that's actually one of the applications possibly of what we have developed, but we didn't try this application yet. It's too early. I mean, not the good time now, for sure. Okay. So anyway, we need, so that's the, that was about beamformer. And now let us, any questions? Hello? No questions? Okay.
I have a question, but I don't think it's important for
Every question
this.
is
It's
important.
just curiosity. Why do we have activity in this gyros between hemispheres when we try to break this?
Yes,
why do we get this?
Yeah, this is a good question. We don't have activity in the gyros between hemispheres, proper to say, but we have activity in the center of the sphere that we use to model the head. Okay. Well, I mean, if you were to superimpose the spheres, and because as I said, the beamformer is looking for something, right? And it has to. Well, this is a trade-off, right? That beamformer achieves. But briefly, to answer this question briefly, is for the sources that are deep, for the sources that are in the center of the sphere, right? See, they're almost radial, right? This because every sensor in the center of the sphere, every source is radial, right? By definition. Because I mean, it just stems from the center, right? If you offset it a little bit, you may have some tangential component, right? So But for the sources which are close to the sensor, this tangential component is small, and therefore the overall topography, the way the source is projected to the sensors, is very weak, is very small. Well, your beamformer has to provide minimum variance for you.
Yes.
And it's, well, why don't I listen to the deep sources? Because they are weak. And what about constraint? Well, constraint will just scale it, and then we will also use, by the way, the synchronous guy to subtract it, and then, you know, that's it. I will take care about minimizing power of the existing source by this, by W transpose, you know, by subtracting the two, right? But then my vector also has some other degrees of freedom, because you have W, which is 102 values. Okay, you constrain, you have only two equations, right? Here, the first source active and the second source active, and they're synchronous. But you have 100 more degrees of freedom you need to satisfy. And it says how to satisfy them. Well, okay, let me listen. Let me tune to the deep sources. Because and the output power will be weak. So that's it. That's what it does.
Okay, thank you. Thank you.
Yeah, okay. So
maybe one more small question about neural activity index. We computed around the location that we have chosen to listen to, which we said that this source will be gain one. Yes. Okay.
I got the question. No, we are not. No, that's the point. We don't know where the source is. Okay, we compute the neural activity index by. Let me plot this this thing for you. Just a second. Let me plot this. Okay, so we compute the neural activity index by comparing the whole brain scan during the post-stim interval, during this interval, to the pre-stim, to the whole brain scan of the pre-stim interval. So see this vector there, here, this guy, QSC post. Yeah, see, it's, let's see how big it is. QSC PST. It's 5003 by 1. It's 5003 locations in the brain we have here. So for each location, we have a value, okay? But it just turns out that it highlights those locations, when of course they're not synchronous, right? Where the sources are, okay? So basically, see, we divide one vector, which is 5003 by 1. Element by element, there is dot divide. See, element dot, this is element by element division. By the same vector, but computed for the pre-stimulus interval. Okay? Did I answer the question?
Maybe I will understand like in 5 minutes.
Okay, you can come back with it. Yes, you can ask again. Yeah, so basically we computed the scan. You can think of this. You can think maybe it will be simpler for you. You are okay. You are doing. Let me show here. You are doing source estimation. Let's say for this time slice. Okay, for instance, for this time slice. Okay, and you have some picture on the brain, right? And then you are doing source estimation for this time slice. Okay, and you have for the entire brain, and then you have another picture. Okay, and then you divide one picture by the other by another picture. Okay. And therefore, those locations which have increased amplitude, they will highlight because, right? And those which have pretty much the same magnitude before the stimulus and post the stimulus, they will stay the same, right? So the only difference is that we are not taking a single point, we are taking the entire time range, and we are computing not just amplitude, but the sum of the squares of this amplitude, okay, which is the power, okay? That's it. So, okay.
One more. I wanted to ask it much time before in our previous lecture. What in this case we had 500 and something sources, and is it the fixed number for each analysis, or
no?
Who determines?
Yeah, well, you determine it. Okay, so see, there are two. Here are two sources, two cortices. Okay, this cortex is low resolution and this cortex is high resolution. But I think they're all low. Okay, compared to the normal one, right? If you let's load them. Okay, let's just load them here. Okay, and then let's look at them. Cortex.
At all sources, you mean?
This is a cortex. Yes, let me explain. I'll explain it. Hold on a second. This is a cortex, okay? Cortex is a parameterization of the cortical surface, okay? It's a triangulated surface where you have triplets, you know, you have points, and each point is connected in a phase, right? You have phase 1, phase 2, phase 3. You know, you can. Let me plot them for you, okay? Just a second. Hold on. I will plot this. Control C. Let's put it here. Okay. Oh yeah, just close all. Okay, so that's your brain. So I'm sorry, I have very, very bad video card here. I mean, not bad, but it's not somehow driving wrong. So see, we have triplets here, right? We have every location here. The surface is represented as a set of faces, triangular shaped planes. Okay, so just planes like this. This is this plane, this plane, this plane. Okay, these nodes are the locations of the sources, okay, what we call sources, okay. In this cortex, in high resolution cortex, it has 5,000 locations, okay. You can downsample it, and in the cortex low, you can see we will have KCT, but it's not really low, okay. It's it's not really high. You have number of it's actually not it's actually not low. It's actually this one is actually much higher, okay. It has 15,000. This one has 15,000 now, so it's just a mistake of what you call low, what you call high. Okay, so in this cortical model you have 15,000 sources, okay. 15,000 vertices, okay. So let's draw it again. Let's draw this CTX low here, CTX low, and let's draw it. So see, this one is much more detailed, right? See, this is much smoother, right? Okay. And I use that 5,000 one for the experiment. But anyway, so the vertices are smaller, and it depends on how well you want to approximate your head surface. Okay, you choose. There is this parameter, the pre-surfer that we use to obtain from MRI this surfaces, right? It can generate up to 300,000 vertices, 400,000. This is a very, very nicely smooth cortex. Okay, you can use this, but it will take forever to compute. Okay, therefore there is a trade-off. And also, if you are moving into the direction of using smaller number of vertices, then the use of arbitrary orientation constraint, basically without fixing removing the orientation constraint, without fixing the constraint, the orientation of a source, the lack of the fixing actually becomes very important, because once you downsample, you simply define fewer points, right, and connect these triangles. Each triangle changes its orientation, and now does not reflect the true curvature of the cortex, okay. Therefore, the orientation, which is orthogonal to the curvature, right, the dendrites, remember those dendrites are orthogonal, it will not reflect the true situation, okay. Therefore, you have to give some freedom, and you have to say that, well, okay, I don't care, I know that the source is there, and I don't care about this orientation, it can be any, okay. Like we did today, find me the orientation, the best orientation. So choose just choose the sum of squares in all orientations. Really, not a big difference. There is a method by Matti Hamalainen at some point he developed, like maybe 8 years ago or 7 years ago, maybe even more. I forgot. But he suggested to constrain the orientation, but do it in a soft way. Draw some cone around what he thinks is true orientation, and allow the algorithm to find the orientation, which is, kind of, it's a trade-off. See, this is a trade-off between 3 sources, and this increases, of course, the number of sources, right? Increases the uncertainty of the problem, right? Because you have 3 more sources instead of 1, right? But so the best way to do it somehow to do some sort of trade-off, right? And the trade-off can be done by restricting it to this cone, not like this, but like this, okay?
Mhm.
Saying that, well, this is also, on the one hand there is a restriction, on the one hand there is some freedom, okay? You know, it's like with kids. So the same story. Okay, so okay, did I answer the question?
Yes, thank you.
Okay, any more? Okay, so we'll move on then, right? Okay, let me stop sharing here. Stop sharing here and take in my hands this beautiful Samsung Galaxy. Yeah. And then let's share the screen here. Hold on. It's now sleeping. Come on, wake up. See, I'm very gentle to it, and maybe it will not. Okay, so that was about beamforming, right? And as I said, this is a method in between the dipole scans, right? The dipole scans and this other method that is, I didn't have enough space here on the right to draw, which we'll study now. It's so-called minimum norm estimation method, okay? This is actually implying the use of slightly different forward model, but it's not like conceptually different. Well, so on the one hand, maybe you could say it is conceptually different, but not really new, okay, for you, to you, okay? See, what we assume in this case, so let's call it MNE, minimum norm estimation, okay? And this method is so widespread that this software that Dasha is teaching you to use is called MNE Python, because it originated from, and it's now in Python, of course, but actually originated from Matti Hamalainen. Matti Hamalainen is one of the key figures in this field. And actually Nastasia is at his should know him or should meet him at some point, I believe. Anyway, so also he's in whatever, anyway, maybe he's at MGH now. Anyway, so the minimum norm estimation is a working course of this entire discipline, okay, because it provides you maybe not the best solutions possible, but it is very reliable, okay? And almost every algorithm uses MNE Python. Every development, every paper compares its result with MNE Python and says, see, MNE Python, not MNE Python, sorry, MNE. See, MNE sucks, but our method works so great, okay? But in practice, the number of methods used is very small, and one of them are actually beamformers and MNE, okay? And those super smart, super duper methods which simulate, which model the sources, introduce a lot of priors, and do some very complicated inference process, and have very like sexy names like champagne or something else. They're not actually used in practice, okay? So MNE, I would say, is an interesting thing. And also MNE, you have to understand it because MNE approach is actually the one that informed development of other more advanced methods, okay? So therefore, it's so okay. So the setting of MNE is, as I said, we have to a little bit modify our model. So we have many sources, okay? Not one, not two, not 10, but as I said, 15,000, okay, or 5,000. Okay, so many, okay? What does it mean, many? Many, you can't say if 2, 10, well, maybe, okay, 2 is okay, but 50, is it many or not so many? Well, it depends on the number of sensors on the one hand, and it depends on the properties of the MEG or EEG forward model, on its smoothness, okay? So see, but I will talk about this later, but now let's just simply formulate the forward model, the observation equation, basically. So for each location, again, you have a topography vector, right? Which is G sub I, and it's GI1, or maybe it's better, you know, this way, G1Y, no, actually not. Oh, yes, G1Y, G2I, G3I, and etc. G number of sensors I. Okay, and those are scalars. Okay. Then you have another. Yeah, this is for a single source. Of course, if you have a triplet of sources, then you have three of these, right? So G1 I X, G1 and etc. Y and Z. But let's just first assume that we have very, very dense cortex, dense model, and we know the orientation very accurately, and therefore, just for simplicity, it really doesn't add anything for now. So, and then from these, you can create a big matrix GI. So where it will be G1, G2, G, and in this case, instead of I, you will have N sources, which is 5,000 of 1,500. Okay. Okay. And this is a matrix. Okay. Because each of this guy is a vector. And this size is number of sensors, and this size is number of sources. Okay. In the M&A setting, it's a non-parametric method. Therefore, you assume that you know the parameters of your sources, and the parameters are location and orientation. Or you, because when you say that there are three of them, you in fact say that you know the location, the orientation, right? But there's just three different orientations of this location. So technically, you can say that you know, right? And then you can interpret already the weights as the orientation of a single source, right? So anyway, so you assume that you know this. No, it assumes that you know it.
You
And
said parametric or non-parametric?
non-parametric. This is non-parametric because you are not looking for these parameters. Okay, we are not looking for R sub i's corresponding to the active sources. Okay, active sources. Okay, we are just measuring their magnitude. Okay, so we know where the source is. All sources. We say that my data. We say basically this. We say that my data X of t is a result of activity of all sources with the time series of each source plus maybe some noise. Okay, and I goes from 1 to n sources, and n sources is very, very large, is much greater than the number of sensors. Okay, you have 100 sensors, you have like, I don't know, 10,000, 5,000, 15,000, or 300,000 sources. Okay, and if you write it in a matrix form, sorry, it's a vector, it's matrix G multiplied by vector S of t, where S is has number of elements equal to the number of sources, and G is number of sensors by the number of sources. Okay, is a matrix. Okay. So in dipole fitting, remember when we fitted dipole and then we said that we wanted to estimate S of t, we were dealing with this situation. We had vector X of t, which was number of sensors height, right? And sense. We had, let's say we had two dipoles, right? We had what? We had G1, G2, right? We had one guy, we had another guy, only two, and many, right? Well, many, 100, right? And then multiplied by S1 and S2. Okay, so we basically had two unknowns in this case, right? But we had many equations. In this case, 102 equations, right? And we were estimated S1 and S2 using the pseudo-inverse approach that I showed to you, which corresponds to finding S1 and S2, which minimizes the difference, right? Squared between these two, right? But this is in a way, I mean, not in a way, this is an overdetermined problem. You have more equations than you need to have, okay, to estimate the two variables, two unknowns, okay? But you say that, well, why don't we stick to this approach? Well, the bad thing is that you need to know this, and to know this, you need to know R1 and R2. And to know this, you have to do music scan And to have music scan, you have to have accurate forward model. And if you even if you don't, okay, if you have reasonably accurate forward model, you get a very spread out scan, and you will need to find those maxima, right? And if your model is not accurate, then the maxima will be in the wrong places, well, and etc. Okay, then the whole story unfolds. All right. So the non-parametric methods don't care about finding these two. They say that my forward matrix G is huge. One topography, another topography, yet another topography, yet another topography, and etc. This. And you have n sources, like 15,000, for instance. Okay. And therefore, your system of equations becomes like this. Many sources, thousands. The corresponding number of columns. Okay.
You said our what becomes like this?
Our matrix, our forward matrix G. Okay, and this one is huge, like thousands, but this one is number of sensors, which is what, 100, 200, 300. Come on. But saying more, this matrix is not even full rank. It's not even full row rank. Because it has a rank deficiency, and therefore, in fact, you can think that in practice you have like about 100 sensors. So you have 100 independent equations, about 10 or 15,000 sources. Okay, so it's equivalent to solving the problem x plus y is equal 10. How many solutions exist? This is a question, and it's not a rhetorical one.
Бесконечное множество.
Yes, infinite number of solutions, because for any x, you can say that then y is equal 10 minus x, right? Okay, can we do anything about it?
Some constraints to
Okay.
have not so many decisions, but
No, but that's the
not so
question.
many
No,
solutions. But
yes, but how? Whatever, anything, any idea.
maybe we can just say that their разница shouldn't be more than something.
Sorry, once again.
Their разница, difference.
Difference. Yeah.
Yes, shouldn't be more than some number. Maybe.
Yeah, good idea. Yes. Yeah, we can simply say, for instance, the simplest solution, we can say that x is pretty much equal to y. For example, why not? You know, and then what? Then x is pretty much equal to y and pretty much equal to 5, right? You know, we are not strict. We are not very strict here, but or we can say that, as you mentioned, as you said, that x minus y is equal to d, right? Some distance. Then, in fact, this is another equation to unknowns, and you can solve it, right? No problem. Or alternatively, you can say that x squared plus y squared is minimum. Okay, so what this means? This means a very interesting thing, actually. You can draw it. X plus y equal 10 is a line, right? Something like this. This is 10, right? This is y, this is x. And you're asking for solution where x squared plus y squared is minimum. What is x squared plus y squared? It's a distance from the center to the line, right? And you want basically out of the whole possible set of solutions, which is, right? For any x, choose x, choose live, choose transported, right? Choose x, choose get y, okay? So, but you look only for this point that is closest to the origin. Why? Well, no particular reason. Just because it's convenient. Because it's something that's better than infinite number of solutions, okay? But in fact, I can answer you why, but to do that, we need to somehow go into the little bit more elaborated presentation using the maximum likelihood and maximum a posteriori estimate ideas, which I will now try to convey to you. Okay. Any questions on this? Is it clear? Is it clear?
Yes, it's clear,
Is
but
it clear? It's clear why this point corresponds to this constraint?
it's clear. But is this the real I don't know ограничение for our solution?
Limitation.
I mean, we were talking, yes, limitation.
Yeah,
were
that's
talking,
yeah. This is a limit. Well, you mean in real life? Can we really look for a solution that has minimum norm?
No, I am talking about this. We are talking about minimum norm. This method, and
Yeah.
Are we considering this case related to our method?
To the brain, of course, yes. We basically what we look in this case. Okay, we have this, okay, and it's hopeless. It's because it's this, okay. It's very fat. Okay, it's hopeless. I mean, it's just hopeless. But you say that, well, the norm of S, let it be minimum. Okay, and then you find a solution to motivate why we're doing this, and more than that, more than that, to show how you can make it more realistic. Okay, how you can introduce, because in a way, this one is some additional information about the source you are looking for, source distribution you are looking for, right? Because you say that I'm looking for a source distribution for the activities of sources such that sum of squares is the smallest. Okay, like bullshit argument could be the brain is a very efficient system. You can read it actually somewhere. The brain is a very efficient system because it doesn't have any redundancy. The activity, it wants to save the power. It wants to reduce the consumption, which is bullshit. Therefore the brain activity has to have the smallest power, and this power is actually the sum of squares. Okay, that one possible argument that you may read in some texts. Okay.
And you said this maximum likelihood, these things, because through them you want to prove that.
Yes, through maximum a posteriori. Yes, through maximum a posteriori. Not because, see, again, this one is, you can think of this, or any other kind of additional information, additional equation about your activity distribution as your a priori information about the sources, okay, about the distribution of sources you are looking for, right? Why a priori? Because it has nothing to do with the data, right? I'm formulated without the data. I'm formulated just based on symbols that denote my source activity. There's no X here, right? I'm just saying that, okay, I want sum of, basically what I want in this case, sum of SI squared be minimum, okay? You may want to say I want sum of SI minus SJ for I and J squared be minimum. Possible. There is such a method also. It gives you very smooth solutions, okay? Because the neighboring sources, of course, there's some modification there, but the neighboring sources will be changing, will be very similar to each other, right? If I and J are close to each other, right? And this summation is within a click, right? Within some. So you have a source, you have its neighbors, and this double summation is for this guy minus this guy minus this guy minus this minus this minus this minus this, but not minus this, okay? And therefore it will create you solutions which are smooth, okay? But anyway, let's just move on here. Let's look for the let's just go to Bayes theorem, okay? Bayes theorem, which tells you, okay, you have X, you have G times S, plus noise. Noise is important here. S of t, n of t. And then you say that what? You say that, okay, you want, this is a probability of S. S is a source distribution, okay? S is a vector. S is a big vector, number of 15,000 or 5,000, okay? Where each element corresponds to a source, right? So, you say that, okay, I want to find such S that this guy is maximized. So the probability of S given your data is maximized. Okay, this is reasonable, right? You observed something, like our brain works, right? You observe something, you observe this data. Okay, so I have a model of what it could be. Like if you're driving in a very dark environment, right? Driving in a very dark environment, and you have certain scenario about what can be around. If, for example, you know that the cars that moving towards you should always have two lights on, then if there is a motorbike or if there is a car with only single light on, you will not be able to recognize this whole thing, right? Because your model doesn't accommodate this, your model doesn't allow for this, right? But what you will do, you will find a solution, your brain will find an explanation of the data that it measures in the context of the model that it has. And if the model doesn't have a car with a single light, then I'm sorry. Okay, so in this case here, the same thing. So we observe the data, we want to find such a distribution of sources that the probability of the distribution given the data is maximized. Okay, so if you write Bayes theorem, okay, so the probability of S given X multiplied by the probability of X is equal to the probability of X given S, which is, I will prove you, this is our forward model basically, multiplied by the probability distribution on sources. Okay, what you just told me is an example. You said that, well, I showed to you like X equal, not X, let's, in this case it will be, of course, it will be, let's say S1 is equal S2, for instance. This will be about this guy, right? Or S1 is almost equal S2. This is probabilistic argument. This will also be about this one. Or sum of S sub I squared has to be minimum. This is also about this one, okay? And about this one is the fact that given S, try to explain the data X. Given S, try to explain the given S, try to explain the data X, okay? And see how much off I am with respect to my model. If I give you the set of sources, do I explain the data? If you don't restrict it, there are infinite number of solutions of S's that will explain X with almost zero error, okay? But you are not interested in everyone, right? You're interested in some specific one. How can I make cancel? Okay, this way. All right. So now it's time for a break.